Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Iodolactonization is an electrophilic cyclization reaction where I2 acts as the electrophile toward a carbon-carbon double bond and an internal carboxylate, formed under basic conditions with NiHCO3, acts as the nucleophile to form a lactone ring via intramolecular attack. Moving on to the next step. Under NiHCO3 conditions, the carboxylic acid is deprotonated to form the carboxylate anion. The substrate is cyclohex-1N1-Vial, acetic acid, which has the double bond endocyclic in the cyclohexene ring and the CH2CO2H group on the sp2 carbon of the double bond. Moving on to the next step. I2 activates the double bond by forming an iodonium ion intermediate. The iodonium bridges across the double bond carbons of the cyclohexene ring. And for the final step, the carboxylate oxygen attacks one of the carbons of the iodonium ion in an anti-fashion, backside attack, SN2-like. The carboxylate carbon is CH2, which is one carbon removed from the double bond carbon bearing the CH2CO2 group. The oxygen attacks the more substituted carbon, the one bearing the CH2CO2 group, which is also the ring junction carbon, following Baldwin's rules for 5-exotate cyclization favored, but here geometry dictates attack at the tertiary more substituted carbon of the iodonium. The nucleophilic carboxylate oxygen attacks the carbon of the cyclohexene ring that is directly attached to the CH2 group, i.e., C1 of cyclohexene, forming a 5-membered lactone ring. Beta-lactone would be 4, gamma-lactone is 5-membered, OCH2C is equal to O with the ring closed through the C1 of cyclohexene. This creates a spirocenter at C1 of the original cyclohexene ring, now bearing the iodine from anti-addition and the oxygen of the lactone. The product is a spiro compound where the iodine and the lactone oxygen are on the same quaternary carbon, the former C1 of cyclohexene, with anti-stereochemistry. The cyclohexane ring and the gamma-butyrolactone ring share this spirocarbon, and iodine is on that spirocarbon. This matches option B, a spirolactone with I at the spiro, quaternary, carbon, 5-membered lactone ring, and intact cyclohexane ring. Why other options fail? Option A shows a double bond remaining in the cyclohexene ring and iodo at the spirocarbon with an unsaturated bicycle. Iodolactonization consumes the double bond, so no remaining alkene is expected as the major product. Option C, no iodine in the product. Iodolactonization always incorporates iodine. This would require loss of I, which doesn't occur under these conditions. Option D shows iodo on the carbon alpha to the carbonyl, EXO to the spirocenter, in a fused ring system. This would require 6-endotate cyclization and different regiochemistry, the 5-exotate pathway. Baldwin's rules favored, giving the spiro product is preferred, and anti-addition places I on the spirocarbon, not on the EXO-carbon. Therefore, the correct answer is B. Therefore, the correct answer is option B.